In this video, we introduce basic concepts about the use of forecasting methods in microgrids and about the use of optimization techniques in a centralized control scheme. We will address the importance of forecasting in microgrids. We will also briefly discuss how an optimization problem can be formulated. Load consumption curves may vary from one day to another, depending on the type of the day, whether it's a weekday, a weekend, or a holiday. They may also vary depending on the season. Even larger changes from one day to another can be seen in the generation curves of renewable energy sources, as they strongly depend on the weather conditions. Forecasting of power consumption and generation is very important in microgrids. A proper forecasting significantly helps to improve the operation of a microgrid. The uncertainty in both demand and supply leads to errors in the forecasted value. This is typically compensated by the power reserve from the generation units. Wind power generation, in particular, is subject to errors in forecasting. Due to the large-scale introduction of wind farms over the past years, power systems were required to allocate higher levels of reserve to cope with these errors. Uncertainty in both demand and supply leads to sharp variations in the forecasted price of electricity. On the top side, we can see the yearly price variations in the electricity market in 2008. On the bottom, variations are shown during a period of 2 weeks. Various parameters such as time of day, weekly and seasonal variations, and volatility affect the forecasting of electricity demand, PV and wind production, heat demand, and electricity prices. Forecasting methods can be classified into quantitative and qualitative methods. Quantitative methods are applied when the historical data of the units is available. Data can be arranged as a numerical time series. In quantitative methods, the future behavior of the process is assumed to be similar to how it was observed in the past. However, this assumption does not hold when important changes occur in influencing factors, for example, climate, behavior of consumers, and electricity market structures. Qualitative methods are used when there is little or no quantitative information available. These methods are mostly based on expert knowledge. Several optimization techniques can be implemented in microgrids. Some of these techniques, such as linear and nonlinear programming, mixed integer programming, stochastic programming, and dynamic programming, have been used in microgrids to solve multi-objective functions, where a trade-off between low operation cost and good energy service is made, for example. The main objective function of such multi-objective optimization problems is based on a combination of environmental costs, such as carbon emissions, capital and operation cost, energy storage costs, like battery and hydrogen storage, and miscellaneous costs. In order to solve an optimization problem, the objective function has to be defined. Some assumptions have to be considered and constraints have to be established. Let's consider an example of a microgrid where the main objective is to maximize the total revenues of the microgrid operator. To formulate and solve the problem, we can consider the following assumptions. The microgrid serves its own need, using the grid when optimal. The microgrid central controller minimizes the microgrid operational cost and is a non-profit organization from which the end users benefit. It does so by lowering electricity prices for end users and protecting them as much as possible from the volatility of market prices. In microgrids, the optimization task can be performed by the so-called aggregator. According to the Energy Efficiency Directive, an aggregator is a demand service provider that combines multiple short-duration consumer loads for sale or auction in organized energy markets. In every optimization problem, there are constraints to which the objective function is subject to. In microgrids, examples of constraints are the technical limits of distributed generation sources, like the minimum and maximum limits of operation, active and reactive power curves, and the startup times. If power exchange with the main grid wants to be avoided, another important constraint can be the active power balance of the microgrid, meaning that the total power generation within the microgrid at the point of common coupling is equal to the power consumption. To sum up, in this lecture, we have seen how various parameters affect the forecasting of electricity demand, renewable energy sources production, heat demand, and electricity prices. We also mentioned the different optimization techniques implemented in microgrids and their objective, being the minimization of environmental, capital, storage, or miscellaneous costs. We also introduced the steps needed for a mathematical formulation of an optimization problem, such as the selection of assumptions, objective function, and constraints. In the next video, we will discuss non-centralized control schemes, namely decentralized and distributed control.